by the team is considered for mathematical science. So today we have the honor to invite Saeed Rastgoo to give a talk. So Rastgoo graduated in 2012 from Universitat de la República. Great. And his specialty is on this quantum gravity and black holes and so on. Okay. So I think, I think people from the physics department and the art department to support us. Okay. So our recording is basically is mostly is weekly on weekly basis. But sometimes we have a team program, like we have to stop and do it again. Okay. Okay, Professor Rastgoo, although so young, he talks a lot of papers and is a leading expert on the field. So let us welcome to the talk. Thank you. Thank you. Okay, thank you very much for being here. I need to stay close to my laptop because of the Zoom. So this today talk is about a general viewpoint of what is non-perturbative canonical quantum gravity. Of course, I have to dismiss a lot of details here and brush over them, but hopefully I can give a rather good picture of the field. And also, what are the implications of loop quantum gravity or canonical non-perturbative quantum gravity about black holes and quantum black holes? So this is the outline of the talk. I just talked about a little bit about quantum gravity in general, and then loop classical gravity, then loop quantum gravity, and then about the black holes. And at the end, if there's enough time, we proposed a new model recently that is framework independent, but captures lots of properties of black holes, quantum black holes that we need. So I talked about that. So let's talk about quantum gravity first. Why do we need quantum gravity, and what is actually quantum gravity? So we all know that when curvature of space-time is large, we need relativistic gravity. I don't know, I can hear my own sound. Muted? What if I mute it? They can't hear me. Anyway. So in relativistic gravity, in high curvature regime, we need relativistic gravity, and that's basically general relativity. On the other hand, if there are okay, so can all of the participants mute themselves? Oh.
Okay. I don't think it's echoing anymore. Say something.
Yeah, I can hear you.
Oh, okay.
Okay. Yeah, there are two laptops. That's coming from somewhere else. I don't know where it's coming from anyway.
Can you just turn the volume off on one of the laptops?
This is a full screen. I don't know how to escape. That's the turtle. And hopefully they can hear me. So if you can hear me, let me know on Zoom. Okay. Let's see how it works. Anyway, no, it doesn't work. The sound is coming from somewhere here. I don't know. Anyway, so I try not to get distracted by this. So Yeah. I turned all the volumes down, but I don't. It's coming from somewhere else. Oh, so you hear my voice twice. Okay, so the small length scale, when we have a small length scale, we need quantum theory for that. We need quantum theory for that, and so this is atomic scales, particle physics, all this stuff. Okay, so what happens if we have both high temperature and small length scales, like in the interior of a black hole close to singularity? So in a very small region of space or space-time, you have both small length scales and really high, or sometimes close to singularity, close to infinite temperature, and that's the combination of these two theories, which is called quantum gravity. If the space is common, is it unknown space locally in custody? Locally, yes. But up to what for small length scale, are we approaching something in question locally? No, but this is at singularity. So first of all, it's been tested up to second order, up to first order actually. So the Riemann-Theory is non-zero. But even with that, closest singularity temperature is really high. Thank you for the question. Okay, so why do we need quantum gravity? So this was what quantum gravity in general is. Why do we need it? First of all, because as we know, we are probably the only species that think about things that are not directly related to survival. Okay. I have to increase this. Is it better now?
I think it's just because you're further away from the laptop.
Oh.
Yeah, I think it's better now you turned it back up. Thanks.
So yeah, so this is one of the reasons, of course, curiosity. The next one is application, of course. But it's funny to have applications, to talk about applications with quantum gravity, and okay. And you see that, for example, most of the advancements of today's world are medical or other computers, everything is due to quantum theory. And quantum theory at the beginning in 1900s, it was just curiosity. People didn't think about applications. And so now it turns out that after 100 years, now we can't live without quantum theory. We have to give up all our technological advancements. So hopefully this is something that quantum gravity will come to help us later, not our own lifetime. Okay, so the other thing that gravitational field is a space-time. Gravity is not just a curvature of space. Gravity is a space-time. The space-time field, which is the metric field, is at the same time describes the gravitational field and the space-time. So we can think about the universe as a bunch of matter fields on top of another field, which is the gravitational field, or a bunch of matter fields on top of a space-time. These are the two equivalent viewpoints of the universe. And so this gravitational field, which is to know that gravity is not a force for this reason also, is not like other forces of nature. This is not like any other matter field that you have out there. And first of all, it's just the background and propagation of other matter fields. So without space-time, of course, we don't have anything to propagate. The typical term is that it couples to all fields in the same way, and that's actually the quantum field theory manifestation of the equivalence principle. And more importantly, metric field or space-time sets the causal structure of the universe. No other field does that. And for example, it tells us what causes what. Because without a structure of space-time, we don't have any. I don't know what I have to do with this. Try to stay close. I can stay close to my laptop. It's okay. Maybe you can move the laptop there. Then you have to put it on the side. No? Hopefully it's better. Anyway, so the causal nature, the causal structure of space-time, causal structure of the universe is set by gravitational field, what causes what. So without that, you don't know. If I give you 2 points on basically anywhere, you don't know which one comes before, which one goes after, present, past, future, and what causes what. You need the metric field to determine that. So that's different. No other field is like that. So because gravity is space-time, quantization of gravity is quantization of space-time at the same, it's equivalent, and it is quantization of the causal structure of the universe. So that's one of the problems that shows itself also mathematically. This is conceptual problem, but you're shaking and making the causal structure of the universe jittery and uncertain. You're introducing uncertainty in the causal structure. So that's one of the issues that we have with quantum gravity. And as I mentioned, because gravity is a space-time, quantization of gravity has far-reaching consequences, as we'll see, about singularities, about everything that has anything to do with space-time, which is about everything in the universe. Okay, so there are approaches to quantum gravity. We can describe them or categorize them in top-down and bottom-up. Top-down is when you have a classical theory and you quantize that, and bottom-up is when you have some substratum, some underlying entity that is not a space-time, and you coarse-grain that and you get a space-time. The coarse-graining is similar to the statistical mechanics and thermodynamics. So you never quantize thermodynamics to get a statistical mechanics. It doesn't work like that. You have a bunch of more fundamental degrees of freedom, atoms and molecules, all this stuff. Some degrees of freedom that are different from the inner degrees of freedom. For molecules and atoms, you have momentum and position. For the gas, the momentum and position doesn't make sense. It's volume and pressure and temperature. But those don't make sense for molecules. So on some lower level, you have something, you coarse-grain it, average over degrees of freedom, etc. And then at the end, you get some picture of fluid, which really, you don't know, it's not fluid, it's not continuous. But you get that, and then degrees of freedom emerge, temperature, pressure, all this stuff from momentum and position. So the same thing goes in the bottom-up approach. In top-down approach, we have perturbative method, which is basically you take the metric. You take the full metric, you write it as a background metric and perturbations. The background metric remains classical, so you keep your classical causal structure. That previous problem is not there anymore. And then you quantize this perturbation. So in linear case, for example, in this gravitational. If you quantize it, you get the particle, the spin 2 particles of gravitons. In non-perturbative case, you quantize. Okay, so in perturbative case, although you keep the causal structure, the problem is that it's not valid for high curvature gravity. It's not because you're just saying that I have a perturbation. If the curvature is very large, you cannot write it as some background plus a perturbation. So it doesn't work for interior of the black holes, for example. In addition to that, it's non-renormalizable as we know it. The non-perturbative approach quantizes the full gravity, full space-time, and that's tricky. That's what loop quantum gravity is about. In this perturbative approach, we have usual quantum field theory approach. The first attempt was this, and then we have a string theory, a superstring theory, although some of them tell that the string theory is not really perturbative. Well, there are arguments about that for and against it. Anyway, in non-perturbative approach, we have loop quantum gravity, we have asymptotic safety, we have causal dynamical triangulation, all of the stuff that some of them are more developed. Loop quantum gravity is more developed compared to other approaches. In the bottom-up approach, my own actually prejudice or idea at the moment is that this is actually the way to go for gravity. Because the reason that we have problems all these 30, 40 years for quantization of gravity is that we are doing it wrong. We are trying to quantize thermodynamics and get the statistical mechanics. Nevertheless, this approach is very hard. So at the same time that I'm working on this approach, I'm also working on this approach. So just who knows which one is the correct one, but the guess is that this is the way to go. And there are two main approaches in this. One of them is called from Wheeler is called it from bit or it from qubit. So it basically says that the information in the universe gives rise to space-time. And information is a very vague term, but that's basically about the entanglement in the Hilbert space and all those stuff. The condensed matter version is that you model your whatever it is below space-time, we don't know what it is, with discrete degrees of freedom. We model them as graphs. So nodes of the graph are the entities that are interacting with each other, and the edges are interactions. We just model it like that. And then you try to get some smooth or continuous, something like a space-time from coordinating that graph and interactions and all. So today I will talk about loop quantum gravity, but first loop classical gravity, what it is. Okay, so the space-time, let's start with the canonical method, because it's a colloquium. I try to be, not to go too fast or too technical. So probably most of you know about canonical method, but let me just go over it quickly. In canonical method, what you do is that you decompose a space-time into a space plus time. So all those attempts of Einstein, everything, they're just going to kind of destroy it again, going back to the picture of a space plus time. But we are not completely destroying the diffeomorphism, the full diffeomorphism invariance of a space-time, because at the end, technically, this is still space-time. Okay, so something happened here. Oops. Okay, so as you see here in this picture, you have the full space-time, this four-dimensional space-time, and we foliate it into spatial hypersurfaces and define some time. So there's a function, there's a time function defined in this full space-time, and that time function is constant on each of these hypersurfaces, but changes from one hypersurface, a spatial hypersurface, to the next one. And so this is the spatial hypersurface corresponding to T1 and all those. Okay, so now our configuration variables are defined on these hypersurfaces, spatial hypersurfaces. They're functions of that space, not the space and time. Well, not the space time. The momenta are momenta of those conjugate momenta, which are derived by derivative of Lagrangian with respect to the velocities. And these degrees of freedom, the Q and P, live on a space called phase space. As we know about that. And the most important structure of phase space is the Poisson bracket. So Poisson bracket gives us the possibility to find time evolution and also find symmetries and gauge symmetries and all that story that we have in all fields of nature. They're all gauge theories, and gauge means symmetry, basically. The evolution itself is generated by the Hamiltonian. Another important piece of information in the canonical method, and of course it is generated by the Poisson bracket, as you see here. Okay, so this is a summary of canonical method. Now, what we do with gravity, what are the degrees of freedom of gravity, how do we do canonical gravity? The oldest approach is taking the space, the system is of course a space-time, it's not a particle or anything, so we are going to deal with the space-time in canonical approach. The oldest approach, you have the metric, spatial metric on those hypersurfaces, three metric. That's your canonical variable, configuration variable, sorry. And the way these hypersurfaces are curved inside the four-dimensional hypersurface, four-dimensional space-time, that is called the extrinsic curvature, and that is related to the momenta of the theory. But there's another approach called the first-order formulation. That's using tetrads and connections. Let's see what these are. So the configuration variable is a connection. What is a connection? Suppose that you want to move this vector in a space-time from here to here. You want to take a derivative. Usually, if the space-time is curved, not usually, always, when the space-time is curved, this derivative depends on the coordinate system. So if you change your coordinate system, this derivative changes. We don't need that. The physics should be coordinate independent. So we add some other term to the derivative, the partial derivative plus some other term. This is like symbolic, so that these two cancel each other. Both of them are coordinate dependent, but such that they cancel the coordinate dependence of each other. And that's called connection, because it connects two vectors at two different points of space-time together, or to anything, not just vectors. Okay, so if you have this vector or object and you want to move it around, either you can solve this equation, or you can define an operator called the holonomy or parallel propagator and act it on the vector at this point, P1, And when you act it, you derive the form of the vector at P2. That's called the holonomy operator or parallel propagator. And parallel propagation basically means that you move the vector such that the component along this curve or in the coordinate system along this curve, the components remain the same. So you get the same vector all over. So this holonomy is very, very important. You'll see later that holonomy is actually the configuration variable of quantum gravity. And why do we use connection? Why do we want to use connection instead of metric? The reason is manifold, but first one is that all other forces of nature are written in terms of connections. Electromagnetism, the degree of freedom is A, the 4 potential, that's a connection. In the weak SU2, that's a U1 connection. In the weak theory, there's this U1 SU2 connection, so there it gives rise to these bosons, basically, and SU3 gives rise to gluons, 8 gluons, because SU3 is 8-dimensional. So why not gravity? Let's write gravity in terms of some connection, and then we can use the methods that we use for other field theories. Okay, so that's the configuration variable of the first order gravity. The momenta turn out to be triads. What is a triad? Because of the equivalence principle, that's one of the questions at the beginning, was that locally you can up to first order in the derivative of the metric, everything is flat, and that's the equivalence principle. Because of that, you can choose at any point, you can choose free or continuous space, free orthogonal or orthonormal basis vectors that have nothing to do with any coordinate system. You can just put them there and work with them. And those are called triads because they're free and they're orthonormal. And you can write metric in terms of these basis vectors. So these are the basis vectors. If we wanted to expand one vector in terms of these triads, you have the vector on the left and the triad on the right. If you have a tensor, which is basically like 2 vectors there, you have 2 triads here. That's why you have. So these triads define geometry. So the knowledge of triad is equivalent to the knowledge of metric. In loop quantum gravity, we'll see later that we just multiplied by the determinant of the metric, determinant of the spatial metric, and this becomes a densitized triad, but that doesn't matter. So these are our momenta. And so why do we, again, so why connections? One of them reasons you heard before, because all the other fields of nature are written in terms of connection. And if you want to couple fermions to gravity, we can't go with metric. We have to go with connection and triads and or tetrads in 4 dimension. It is similar to the formulation of other field theories, and also in standard quantization, if you take the full metric and you want to quantize it, that's called geometry dynamics. That turned out to be a disaster because you cannot even define the Hilbert space. The Hilbert space is ill-defined because of the inner product cannot be well-defined. And for in metric variables, you cannot quantize gravity non-perturbatively without, taking some part of the metric out. Okay, so how do we go about loop quantum or loop classical gravity and write for the classical formula? We start with an action. This first action is called the Palatine Action. These objects here, these are tetrads, the 4-dimensional version of those triads. So they carry information about the geometry. This is the volume form here. And this F is the curvature of that connection. The curvature of that connection, that are some connection related to the gravitational field, that carries the same information as the Riemann tensor. So instead of writing the Einstein-Hilbert action, which has rich scalar units, we write it in terms of this curvature.
I didn't quite understand why you said that if you try to do standard canonical quantization with the triad and then the metric, why that didn't work?
Then not the triad, just with the metric and extrinsic curvature. That was the first version. It doesn't work because of the Hilbert space is ill-defined. You cannot define an inner product for that Hilbert space. It's worse than, so yeah, it's one of the things that it's not positive, but there are other issues with that we can't define the Hilbert space. Yes. Okay, so this thanks for the question. And this the first action, the Palatine. So you see that basically curvature and volume here. And this is, we can show that this is equivalent to the usual Einstein-Hilbert action of relativity, gravity. The second term is just a topological term. Basically means that if you find the equations of motion, this has nothing to do with equations of motion, the second term. It just classically is irrelevant. That this term is added by this 1 over gamma coupling constant, as you see here. And this, again, classically is not important, but in quantum mechanics, in loop quantum gravity, it sets, this gamma sets the minimum area that you have. So area is quantized in loop quantum gravity, and this sets that area. Okay, so you just go ahead, perform canonical.
Equation of motion with constant geometry of the spacetime. You have a topology.
Think of it as a boundary term. The boundary terms don't affect. Now you go ahead and do the canonical analysis, find your momenta, configuration variables, and then write everything down. And you will see that the configuration variable becomes something which is called the Ashtekar-Barbero connection. So it's not, the detail is not important, but this is related to the extrinsic curvature of those foliations that I showed you. And this is some sort of connection to move SU2 objects around. Again, that doesn't matter. But you have a space-time index here, A, and a SU2 index here, I. So this is an SU2 valued vector, a three-dimensional vector. Okay, so this is our base variable or configuration variable. And the momentum, as you remember, it was the density times triad. So those the three orthonormal vectors that define the geometry, have information about the geometry.
So where did that SU2 come from?
That's become because of the freedom of the Lorentz freedom of the rotation. This is SO3 rotation in space, but SU2 is the double cover of SO3, so that's related to the freedom in rotation. Okay, so the canonical algebra comes between these two. Obviously, if you have anything, it's delta of the positions in a space and delta of those ij and ab. And that's the classical theory until now. Now we want to move to something more like having more information about the curvature of space-time. So before moving on, let me tell you what is the Riemann curvature tensor. So Riemann curvature tensor has all the information about curvature in space-time, and that's the important object we work with in usual metric gravity. So how do you compute that or find that? We start with a vector here and take it and move around the loop here, this blue loop, and come back, like as you see here. And if it gets back parallel transported, it gets back in the same form of the vector, it means that there is no curvature. Riemann tensor is 0. But you see that when it comes back, actually when it gets close, I will stop this. There, here, you see, when it comes back in a loop, parallel transported, they are not the same. So that shows you there is intrinsic curvature there. So the Riemann tensor is related to that that loop and how you do this parallel transport. But you have to take the shrink there, technically, mathematically, you have to shrink that loop, that triangle, blue triangle that you see here, to 0 area. And then you will find that the difference between this vector, final version of the vector, and initial vector of the vector is proportional to the Riemann tensor. Okay, so we know that loops are very important already. And these are different from loops of quantum field theory that come from the Feynman diagrams, but these are space-time loops. Okay, so the question is that can we get information about the curvature Riemann tensor from the connection instead of, so we don't want to use the metric variables, so we want to use the connection, so we can't use Riemann tensor. We want to use connection. So is there any object that gives us the geometric information of the Riemann tensor, but it is in terms of connection? Yes, it's the constraint holonomy. So the holonomy is an interesting object because its trace is called also the Wilson loop in quantum field theory, and it has, okay, let me tell you in the next slide. So this is the form of the holonomy, very kind of like not nice looking object, but it's basically an exponential of an integral over E. This E is a curve, so it could be this blue curve, right? Could be a loop or could not be a loop, I mean, just a curve in a space, you take the integral of the connection, and this is the just SU2 basis, because it should be here because of the A is an SU2 object. This is the tangent vector to the curve, and this is the parameter of the curve. So basically, you take the connection, take its integral over the curve, exponentiate it, and that's your holonomy. This is a path order exponential. Actually, it's an infinite series, but you can think of it as exponential of that integral of connection over the curve. And that is the same thing that as parallel propagator. Okay, so there's an important theorem called Gauss theorem that tells us that the trace of this holonomy, this is actually coming from quantum field theory. The trace of this holonomy has, if you have all the holonomies of all the loops in the manifold, it has information about all the gauge invariants observables in your theory. Maybe in a more simple language, it says that all information about the Riemann curvature can be obtained from the holonomy, which is related to the connection. So I don't want to use Riemann curvature. I just want to use the connection. So I compute the holonomy, and this object has all the information about geometry. Okay. So now we are in loop variables. So now we know what we want to do. So in loop classical gravity, our configuration variables are holonomies. Our momenta are the smeared version or the flux of the, remember the three vectors, those over some area. The reason that we smear them is technical, but so basically we don't want direct delta functions and all this stuff. And the algebra between them is the Poisson bracket is called the holonomy flux algebra. So a holonomy configuration variable and a flux, shear flux of these densified triads. So this is our algebra. And this theory is called loop classical gravity. Remember, I moved from the metric to the connection, but I didn't stay in the connection. I moved from connection to the holonomy. My connection is not my canonical configuration variable anymore. So metric, connection, no, holonomy. And now my momentum is the three vectors, orthonormal vectors, flux of them over any area. Okay, so we have just changed the variables, just played with the variables. Nothing is changed. The classical theory could be exactly the same as the Einstein gravity, but the devil is in the quantization. What happens that the physics is actually different in quantization. Okay, so let's go to the quantization. Now look quantum gravity. What is quantization? In layman terms, it's introducing uncertainty into the theory, right? So your quantities and observables would be uncertain. Two of them cannot be measured at the same time. They are incompatible ones. And quantum mechanics does it to systems with finite degrees of freedom. Quantum field theory does it to systems with infinite degrees of freedom and relativistic. And relativistic quantum mechanics does it to relativistic systems with finite degrees of freedom. So this is what we basically do. So we run some sort of field theory or quantum field theory related to this connection. Okay, so this is the quantization. In a little bit more technical term, you have the phase space, which was your holonomy and the triad, the flux. In phase space, you have Q and P variables, you have the Hamiltonian, Poisson bracket, observables, time derivative. And quantization, in technical terms, is a representation. So you take this Q and you say that I want to represent it or write it as an operator on a certain Hilbert space. How do I do that? There are many ways to do that. This is called the quantization. And the uncertainty arises because you go from the Poisson bracket to the commutator. And that's where you introduce the uncertainty in your system. This is where like layman version of the uncertainty comes from. So you do this representation. There may be different representation of how you can present your, write T as an operator, for example. And some of them may be unitarily inequivalent in the sense that physics is completely different in this representation and that representation. Although the classical theory was the same, but if you represent them differently, your quantum result will be different. And that's why loop quantum gravity is different from all other quantum theories, because its representation is different and unique. Okay, so remember that our classical variables were holonomies. Now we put a hat on top of them, represent them. The fluxes also represent them. And there is a very important thing in loop quantum gravity Hilbert space is that we don't have the operator corresponding to the connection. We only have operator corresponding to holonomy. For mathematicians in the audience, this is because the representation is not weakly continuous. We cannot represent A. You have to represent an exponential version of that. But at the end, we can discuss that if you want. So the A itself, the connection, remember, it's like Q. What does Q in the X, for example, in quantum mechanics, what does X generate, or P? P generates X, infinitesimal X transformation in the X. And X generates infinitesimal transformations in P, right? So A generates infinitesimal transformations in geometry, in Is, in those three triads, right? However, this doesn't exist. So we don't have infinitesimal change of or transformation of the geometry. We only have these exponentials. These are group numbers. These all only generate finite transformations, right? So this means that you cannot change geometry infinitesimally. So it just goes like that. That's the quantization of geometry. That's the root, basically. And that's why the representation of quantum gravity is different, and this representation makes all the difference. So I've talked about all of these. And the loop representation, as I mentioned, is inequivalent to the Schrödinger representation. There's some technical stuff there. So we get fundamental.
So what is the Hilbert space?
You mean the states? Or
Do you have anything concrete in mind for the Hilbert space?
yes, I will show the states what they are, and then that's a good question. Okay, so there, the states. In quantum mechanics, when you have states, what you have Q and P, X and P, right? Your psi the state function is a function of either X or P, half of the phase space. What is the half of phase space in this case is holonomy. The other half is the flux. So either canonical configuration variables or moment graph. We write our psi as functions of configuration variables. So it can be a function of one holonomy, two holonomies around one loop, two loop, or one curve, two curve. You can have n of them, right? So this is just like folk quantization when you have one particle system, two particle Hilbert space, three particle, and then you divide them together and tensor product and everything to get anything you want. So we have the same. So you can write it with one holonomy state. We have two holonomies, and this is a map from SU2 objects, is holonomies where SU2 objects, two complex numbers. And how you can imagine this, how you can picture this as a graph. Because think about that, this E1 is a curve in a space, and you're integrating over that to get a holonomy. There's another curve, there's another curve, so E1, E2, up to En. And these, at some point, they connect to each other, and cut each other, and you can imagine that as a graph. But these holonomies are SU2 objects, so they carry SU2 labels, 1/2, 3/2. Yes? Right. It is, but it is diffeomorphism invariant. That's the difference. The lattice is just rigid. This is, yeah. No, there is nothing fixed. That's the background independent of the quantum. Yeah. So, but it is like a lattice because lattice is usually a graph. A graph. Yeah, exactly. A graph with labels like this. So this. The wave function is the state of spatial hypersurface at any point in time. So it gives like a state that in quantum field theory gives the matter content, information of the matter content. In loop quantum gravity, we are not at the moment dealing with matter content, just a space-time. And each state, the one of these spin networks that you see there are called spin networks. These give you about information about this space. Does it have a black hole? Is it curved like that? Is it curved the other way? All this information is inside psi. Okay? And this is called a spin network. And the spin network is a basis vector or basis of the Hilbert space of loop quantum gravity. So you can superpose these together and get different spatial hypersurfaces. So you can superpose it so that you get a flat universe. Superpose them so that you get a universe with two black holes. Just like quantum field theory, that you have different states and superpose them to get different contents of matter, it's the same way. So this is the Hilbert space. We know how it works. Yes.
Could you explain it again, maybe? So why don't we represent usual wave functions by graphs?
Because usual wave functions are just so you need quantum field theory.
Or quantum mechanics, like many body wave function. Why don't I draw a graph then? Oh, we don't think about it in terms of graphs.
Right, because those are functions of, depends on the representation, but those are functions of position. For example, quantum mechanics, those are functions of positions of objects. And that we cannot think about that as graphs. But these are like one-dimensional objects, curves, these h's here. So canonical variable, configuration variable. It's not like an x, it's a one-dimensional object. Extended object. And then you can think of that as a graph. Does that make sense?
What are these numbers? 2, 1?
Oh, these are because these are SU2 objects. They each carry an SU2 label, right? You can have holonomics, but one half label, SU2 label, or any label that you want. But that I, small I index, you remember that was. And these are those labels, SU2 labels.
Any origin?
No. You can have like you have many particle systems. You can make them. So you have a graph just with one edge, a graph with two edges, and you can combine them, and you get like a complicated thing. Just like the Fock quantization that you have one particle system, two particle systems, so you have one edge system, two edge systems. Of course, in a space-time, if you want to deal with space-time, you have to have a lot of. But yeah, so this is that basically.
But n edges, can I vary the number of vertices in that graph?
Yes. So the number of vertices is basically related to n. So
Cannot change.
you cannot change that, but you can again. So you have different ends than proposed. But you can erase and add edges. So, but that's by dynamics, not just kinematically, just there. It depends on. So you mean in space, or I mean you can the same thing that you can do with the Fock quantization. That if you want many particles, you just you have to multiplication and addition of a tensor product and tensor addition of these states, and you can do that with here too. So you can have as much as you want a space with large number of edges. And indeed, the space should be like that because it should look continuous. So you have to superpose lots of these things together.
So could there be dangling edges that are not connected?
No, all of them should be. So that's one of the conditions we put on. So all should be. You cannot have an open-ended edge. Yeah.
Involve a part integral of all possible metrics, then you can cut that open and define your Hilbert space as one particular time slice. So if you do that, can you find the same find space like this? Can you come to this picture from that perspective?
I'm not sure, but that approach is a different approach. So you sum over all geometries and all topologies to get your space-time. In spirit, it's the same because you're summing over some sort of geometries. But this picture, I don't think that's you can use that.
So what generates the kinetics for this picture?
Like dynamics, you mean?
Yeah,
you will see in a moment. Yes. Okay, so this is the states, and these are really interesting questions. Thanks. So these are the states of basis states of loop quantum gravity, and you already have an insight into what a space is. And a space is you're kind of you might think that the space underlying a space is a graph, but maybe the better interpretation is that the same way if I ask you what is psi in quantum mechanics, where is it? So it's not there. It's something complex, right? It's a complex function. It's a mathematical entity from which physical reality emerges. You can get it, construct physical reality. So a space as a physical thing out there can be constructed out of these spin networks. You can think of a spin network being underlying the space, but the better idea is that just mathematics gives rise to physics, which is quite a philosophical statement. Anyway, so this is the basis, the spin network. And the picture, as I mentioned, is that the smooth space-time is in reality not smooth, and it's constructed out of these discrete objects. Okay, so we are getting near the end of the loop quantum gravity part. Hopefully we have time. Okay. Now the loop quantum gravity actually gives rise to nice observations. One of them is that area is quantized. So space is quantized, but area is quantized. The way to see that is that if you choose some area in a special hypersurface and you look at the graph that represents that space, and you choose some part of that space, just this part, and look how many of these edges of those that the spin network has punctured that area, and the number of the punctures, basically, as you see here, or the spin labels related to those punctures, which is very similar to angular momentum, as you see here. This defines the area. So if you have a very like a graph that only has a few edges, that's highly quantum because the area is very close to the Planck length square. In order to get a really smooth spacetime, you need to superpose lots of them, get lots of these edges punctured, a small area, and then you get kind of a continuous area. And you see that if I have 10 billions of these edges puncturing this area, the difference between 10 billion and 10 billion and 1 is nothing, basically. It's very small, so you can't perceive that discreteness. It's like that hydrogen atom. So you go higher, the distance between the energies becomes negligible. So in order to see this, you need to have a really large kind of glass, magnetic glass, not magnetic glass, sorry, magnifying glass to see this discreteness. And the minimum area is also Planck length square. The same happens to the volume. So suppose that I choose some volume in space, this is sphere, and I look into the volume, how many of these nodes you see inside this, the number of nodes inside that, plus multiplied by some of those j's that we saw, they define or they give you the volume. The volume is also quantized, and the minimum is Planck cube, and so that's how spin networks work. Give you the area and the volume of the space. Okay, so I don't know how much I have time. 15. Okay. So what do we do with black holes? What you do is that you start writing the Hamiltonian of the full gravity, and then you reduce it to the Hamiltonian of that black hole by choosing the metric of that black hole. So some metrics are more simplified and make the Hamiltonian more simplified. Then you go on and find the densitized triad, you go on and find the spin connection, extrinsic curvature, and using that too, you find the Ashtekar connection. So you write everything there. And the important thing is that in the Hamiltonian, there's always a curvature term. Remember, there was also in the Lagrangian. And that curvature term is to be computed using these loops. Again, remember those loops to compute the curvature. And we compute the curvature, you remember, using holonomies by connection. The important thing is that you cannot take in quantum version, you cannot take the limit of those loops, the area of those loops going to 0. That's the difference loop quantum gravity makes with other approaches. Because you cannot go to 0, because there's a minimum area there, all sorts of a Pandora box opens and all sorts of stuff happens. So you compute the curvature in that Hamiltonian of the black hole using these loops. Then you quantize that. All of these, one of my students, for example, is working in one of these things, and now it's 1 month he's just producing 200 pages of computation. So it's just over this one slide is worth probably 200, 300 pages of computation. Okay, so there are different procedures, a little bit different in the community. It doesn't matter. What happens is that, so suppose that I get the Schwarzschild black hole, do this for it, and then I get Hamiltonian. And then I look at the Hamiltonian inside the black hole, not the outside. Remove the outside. And it turns out that the inside of the black hole, I only get a system with finite degrees of freedom, just 2 degrees of freedom. Really 1, actually. And that 2 degrees of freedom is a cosmological model. In physics, when we say cosmological model, we mean a model with finite degrees of freedom. In the universe, we only have the scale factor, for example. So it's much easier to deal with this rather than field theory. Field theory has infinite number of degrees of freedom. Now, what we can do is that take that Hamiltonian and study the congruence of geodesics. Suppose that I have 10 particles in a circle, and they're moving in space and time. And by studying them, actually Penrose and Hawking, that's how a singularity theory is thinking around. You study if they're getting closer to each other while they move or getting farther from each other. If they're getting closer to each other, gravity is getting stronger and stronger, and at some point they focus infinitely, and that's where singularity is. That's the definition of singularity. If they kind of the lines of particles, as you see here, reach a focal point. Of course, sometimes this is just a coordinate problem, but many of the times it's a physical result. Okay, so that thing I told you, this getting closer or further, that's called the expansion scalar. So it tells you what is the distance between these objects when they move on a space-time. So the distance is now decreasing, so expansion scalar is negative. Basically, it's not expanding, it's contracting. And the rate of change of this expansion is also important. And if both of them are infinite or negative infinity, this means that we have singularity. If both of them are finite, it means that just objects are going around and there's no singularity, everything is fine. You also can study the Kretschmann scalar, which actually tells you what is the curvature of a spacetime at some point. Now, it turns out that in classical gravity, in Schwarzschild spacetime, you see the expansion goes to minus infinity. When you get, there's the horizon, this is the center of the black hole, and when you get from horizon to the center of the black hole, the expansion becomes negative, then it becomes infinitely negative. So there's a singularity there classically. However, when you apply loop quantum gravity, what happens is that until close to the singularity, everything is classical. Like classical behavior is the dominant. But the quantum effects kick in and then turns everything around, and you get zero expansion. So singularity is resolved in this way. The close-up is on the right-hand side. This is basically this part. See that the expansion actually becomes zero, so there's no singularity there. The rate of expansion of the rate of change of expansion itself also, classically, you see the red curve goes to minus infinity, loop quantum gravity goes to zero, so no singularity. To double check that, we compute the Kretschmann scalar. Kretschmann scalar goes to infinity, not minus infinity. It goes to infinity at the singularity. See the close-up in loop quantum gravity at the singularity is just, it doesn't go up. It wants to go up, but the quantum effects turn everything back. And then there's no slope. Like 3 pieces of evidence that there is no singularity in this model. Okay, so last thing about this quantum thing, that think about this red curve and the blue curve as classical. The blue one is the classical, red one is the quantum version or effective version of the radius of these objects that are falling in, basically, or how they get getting close to each other. So you see that classically these objects get closer and closer, and the distance between them becomes zero under singularity. Quantum mechanically, it's a bounce. So objects go into black holes, get close to each other, then go up. And that bounce, from this point, we interpret that as a white hole. So things start going up instead of going in, and this is called a black hole to white hole bounce. And loop quantum gravity, most of the models in loop quantum gravity predict that. Of course, this bounce takes a long time because of the difference between the perception of time inside the black hole and outside. But there's a bounce there. So with this, I get to the last part of the talk, which is something that is framework independent, have nothing to do with loop quantum gravity. What we get our lesson from loop quantum gravity and other approaches, and the lesson is that it seems that the black hole's singularity should be resolved, and it seems that bounce is there, so there should be some bounce. The black hole, the objects go in and come out, and the singularity is just removed from space-time, and the black hole is just evaporated. So we suggested a model, and that model is this. So this is a metric, the Schwarzschild metric, the same as Schwarzschild metric. The only difference is that my mass here is time and space dependent. It's not constant. In Schwarzschild, you have a constant mass. Okay, so the mass function, we define it like that. Why do we put tangent hyperbolics there? Tangent hyperbolic, if you think about it, it goes from -1 to +1 like that, or 0 to, or depends on how 1 to a tangent hyperbolic. So it kind of gives you a bounce. Whatever you have, it goes from something to the other way. And this here gives me a bounce in, this is a velocity, bounce in velocity. So you have a velocity of objects going in, and then velocity becomes zero, they come back out. And as you see here, the green curve describes the mass. So this is a mass function. That's why it is model independent. You see, close to the 0 point, the center of whatever the coordinate system we have, there's no mass. Then the mass increases gradually. So it's like a spherical shell. And this shell is going forward and coming backward. But at the center, there's this shell, there's no matter at all. So this shell is going forward and backward. This L naught is a scale just for dimensional analysis. The R naught is the position where the bounce happens, right? The M naught here that you see, this basically scales the mass of the black hole. If you look at the black hole from far away, that's called the mass of the black hole. That's called the ADN mass, and that sets the scale there. The density is given by derivative of mass with respect to r, well, in spherical coordinates basically. And you see the density now here, the red curve. So you see you start from t minus 1500. So basically the plot goes like this, from left again coming down and going to the right. So you see that the density is increasing, and at the point of bounce it increases the maximum here. So you have to think of it as a three-dimensional or rotate this curve. And again, it goes backwards and goes out. So the density comes in, becomes large, and goes back. And this is a three-dimensional view of the density. So it starts from here, goes close to 0, but doesn't reach 0. It becomes larger and larger here, gets a bounce. It doesn't go to infinite at 0 and goes out. So this is the viewpoint of what we have. And that was the density, and these things are really not important. Other parameters. One important thing here is the velocity. You see the velocity here. This velocity is the velocity of falling in and going out. And that velocity depends on, of course, the tangent hyperbolic of time, but there's an n here. That n is very important because it decides about the mass of the lifetime of the black hole, how long it takes for the black hole to form and disappear. And by choosing that carefully, we can actually produce different results from different people. One of them, our own Don page, that has the lifetime of the black hole. It goes with, actually, Hawking and Don. It goes with m cubed, so we can produce that too by choosing this n equal to 2. And so this is the numerical results. What happens is that at this point in time, here, this is the initial time, we go up, and this is the space. Suddenly, two horizons appear, not one horizon. Schwarzschild black hole has one horizon, but in this model, we have two horizons. And the red one, which is the exterior horizon, that almost for all the time remains null, which is all the horizons should be, the usual classical horizons. At the beginning, it's not null, of course. It's a little bit time-like, becomes null, at the end becomes a space-like. But there's an inner horizon, and inner horizon is closed from our view by the outer horizon. And this inner horizon actually moves in. So that's the 0 point. Two horizons form here. This horizon stays here. That horizon goes in. And that horizon is not null. Here it is time-like, then becomes a space-like. Then there's a bounce. This horizon comes out and matches outside the exterior horizon, and it disappears. So you have a bubble here, and anything inside this red line is the black hole, right? And the green line here is the density, peak of the density that you saw. So that's the density of going in and coming out. And interestingly, at some point, it goes inside between the two horizons and then comes out. And in order to go in between the two horizons, it has to go faster than the speed of light. And this is something that happens in our model. At the same time, this is something we have to think more about it. But remember that this is a highly quantum regime at this point. So maybe effective interpretations may not be the best. Now, this is the causal structure. So I go back again. So look at the region 1 here. Region 1 is this one. These are the light ones. So you see that this is null, this is not null. And you can see all these regions. Sorry, you can see all these regions in the slide and find the causal structure. It turns out that the model is behaving very strangely, and as it should, close to the bounds. So probably one of the final pictures. This is the one before the last slide. This one is the Penrose diagram of this black hole. So you have a bubble here. That bubble is the black hole. So the matter, the blue line goes in, creates a black hole. The black hole, these two are the horizons, red one outside and the curve red inside. You have two horizons, that they come back, disappear, and the black hole is gone. So we don't have any singularity. We have a black hole that bounces, the non-singular black hole with bounce. And this picture is actually computed, not just guessed. So as you saw, this is basically this picture, which is computed from our model. Finally, this is about what I talked about, the lifetime of a black hole. So the lifetime of the black hole turns out to be this formula, and this is the mass of the black hole. And it turns out that, for example, for Hawking and Don that have this lifetime going as m cubed, you can just simply choose your velocity here, n as 2, the number 2, so the speed of the going in and going out, and you get something m cubed. You can produce with this model any other lifetime you want. If a string theory gives this loop quantum gravity, so this is quite firmly independent. And so basically that's it. So as a summary, I talked about loop quantum gravity in general, which is a final theory of nature, hopefully we think. And it has 4 recent consequences about black holes, quantum cosmology, everything we want to know about the nature, hopefully again. And then I talked about loop quantum gravity and showed that it shows that singularities are removed. I didn't talk about that, but in cosmology also remove the singularities in loop quantum cosmology. It has interesting predictions about the spacetime, the discreteness of area, volume, even length that I didn't discuss here. But loop quantum gravity, like any other theory of quantum gravity now, is not complete. So we are still looking to find a full theory. Maybe we're combining several ideas from several theories. And finally, because loop quantum gravity predicts that there's a bounce in black hole to white hole and singularity is removed, we propose the model, framework independent, not from loop quantum gravity, that produces a evaporating black hole, non-singular and bouncing. And that shows very promising predictions, and we think that this should be very close to what any full theory of quantum gravity could predict, because black holes should not have singularities, and most probably they are not eternal. So this model should capture most of those properties. Okay, and thank you very much.
So now that the space